In this video, we're going to discuss laws of motion and eventually talk about force. Now, there is going to be a lot of text in this video, so if you see a green check mark, that means you should write down what's on the screen. But if you see a red X, then you don't really need to write it down, just sort of try to follow along so you can help yourself understand the concept. The ancient Greek philosopher Aristotle taught that all objects tend towards rest, because objects want to be at rest. So if you kick a rock, it eventually is going to skid to a stop because the natural motion of that rock is at rest. It doesn't want to move, it wants to stop moving. Therefore, for an object to move, something must push or pull it. So if you see a rock moving to the left or moving to the right, something has to be physically touching it in order to push it so that it can move. Now, this is sort of like our basic, our gut understanding of what motion is. And it kind of works. Like if I have a small frictionless car and I want it to move, then I'm going to have to push it, right? Okay, yeah, so if I push the cart, it's going to move. But so here's the thing. What about if I was to push the cart and then stop pushing it? It continues to move even though I'm not pushing the cart. How do things move without being pushed? Like if I push a chair down the hallway, it eventually will come to a stop, but how is it moving when I'm not pushing it? Well, Aristotle and his followers had a really hard time explaining this, and eventually it got to the point where medieval philosophers were suggesting that an invisible hand emanated out of the person who was pushing the objects until it was so far away that the push sort of like faded. Super weird, and also not really a good explanation of what's going on. So let's just go ahead and call it, this is wrong. Aristotle's view of motion is wrong. Objects can totally move without being pushed. So something else has to be going on here. Galileo Galilei was the first person to really challenge Aristotle's thinking. And in a book called Two New Sciences, he said that really it's friction that's making all of this very hard for us to see. And if you have something really heavy, like, say, a bowling ball, then it's going to continue to move, and it is not going to tend towards rest. Because that object wants to move. Rest is not natural to it. And in order for that object to come to a stop, something has to stop it. That could be a wall, a big block, or eventually maybe it could be like air resistance and some friction. So, in this work, Galileo sets this new idea for us. He says an object will continue to move until it is stopped. And this is different from what Aristotle says, because Aristotle says things have to be pushed to move. And Galileo's like, no. If you want something to stop moving, you push it. But its motion does not need to be explained. You don't have to keep pushing the bowling ball in order for it to move forward. It just moves forward. Right after Galileo, the French philosopher René Descartes also sort of said the same thing. He hated Aristotle, so he wrote this book called Principles of Philosophy. And in this book, did I say he hated Aristotle? He wanted to replace all of Aristotle's thinking. And he very famously said that objects are moving, and they naturally move with constant speed in a straight line. So this is just what Galileo said. Only Descartes is kind of like formally clarifying for us that all objects are moving with a constant speed in a straight line or in one direction. Now, Descartes is also the inspiration for Zooey Deschanel. To recap, Galileo and Descartes' perspective on motion is very straightforward. They disagree with Aristotle, and they say that moving objects do not tend towards rest. Instead, friction, some outside action, is what is responsible for that stopping. If you remove friction, then an object will just move forever with a constant speed in a straight line. Now, this also means that objects can move without being pushed or pulled. So this is a more appropriate idea of motion and what's happening when you see something moving without an object pushing it. There's no ghost. It's just moving because motion is a natural thing. Now, after Galileo and Descartes comes Isaac Newton. Isaac Newton is like the greatest philosopher in the world of math and physics. And he's a boss. He takes all of the thinking in Principles of Philosophy that René Descartes wrote, and he writes an expanded work called Mathematical Principles of Natural Philosophy. And in Mathematical Principles of Natural Philosophy, or as it is often called, the Principia, he suggests that we should define this concept that Galileo and Descartes have come up with about motion. He calls it inertia. And then he also lays out some official laws of motion, which is what we're going to take a look at now. So let's start with inertia. At the beginning of the book, Newton defines certain words, and he starts with this word inertia. And this is basically just a formal definition of what Descartes was saying. All objects move with a constant velocity in a straight line. He says, a power of resisting by which every body endeavors to persevere in its present state, whether it be of rest or of moving uniformly forward in a right line. Okay, so that's exactly what he said. How do we sort of summarize this information? Well, we call this mass. We say that all objects move with a constant speed in a straight line, and mass is a measure of an object's ability to resist change in that motion. This is often known as inertial mass, but mass really is a measure of an object's inertia, or its ability to continue moving in a constant speed in one direction. Okay, so now let's talk about the standard ability to resist change in motion, or what's known as 1 kilogram. 1 kilogram is the standard measure of an object's ability to resist change in motion. And 1 kilogram is literally a thing. It's the kilogram. Like there is a kilogram. It is a metal cylinder, and it's a thing. It's kept in a units and measurements facility in somewhere near France, and it is the standard ability. If you want to talk about an object being able to resist change in motion, then you have to reference this kilogram that's in France. It's known as La Grande K, or the Big K. Now, this kilogram is actually technically a prototype because it's housed in 3 vacuum-sealed bell jars, because it can only be the kilogram after it has been washed to remove surface contamination, because bacteria has mass, and if it gets bacteria on it, then it actually has more mass, and therefore it's not the kilogram anymore. We're working on something better. Okay, so to remind us, when we say change of motion, we mean acceleration, or speeding up, slowing down, changing directions. The kilogram, inertial mass, it's a measure of an object's ability to resist this, to resist speeding up, to resist slowing down, and to resist change in direction. So let's consider what this means for an object with more mass. If an object has more mass, like think if you were to kick a bowling ball and a little tiny kickball. If an object has more mass, then it's going to experience less change in motion because it has more ability to resist change in motion. And if it has less mass, then there's going to be more change in motion. So if you kick a bowling ball and a kickball with the same force, then the bowling ball will experience less change in motion because it has more mass. The kickball will experience more change in motion because it has less mass. After defining inertia, Isaac Newton discusses the 3 laws of motion. Each law of motion will tell us something about force. So what I want you to do is draw a big box, taking it maybe a half or a third of the page. And on the left side of the box, write law of motion. And on the right, write what is force? We're going to use this box to help us keep track of what the law of motion is trying to tell us about motion, and then how that enlightens our perspective of force. Let's start with the first law of motion. Isaac Newton literally said that every body perseveres in its state of rest or of uniform motion in a right line, unless it is compelled to change that state by force. So let's take a look at an example of this. The way that we normally define this is we say that an object will travel with a constant velocity unless acted on by a force. So in this video, these guys are known as the Dudesons. They're on top of this car and they're moving towards this concrete barrier. They both have velocities. The Dudesons have a velocity and the car has a velocity. Then the car hits the barrier. Or the barrier hits the car? I don't know. Anyway, the car experiences a force and therefore an acceleration or a change in its motion, and the velocity of the car reduces to zero. But what happens to the dudesons? Well, nothing changes their velocity, so they just continue forward with that velocity because they were not acted upon by a force. That's the first law of motion. So let's put this in our box. Number one, an object will travel with a constant velocity unless acted on by a force. So let's kind of rephrase this concept and think, what does that tell us about force? Well, force changes motion. So let's write that on the right side. Force changes motion. Now, this is important because force does not cause motion, it changes it. It causes something to slow down, it causes something to speed up, or it can cause something to change its direction. But it is not the actual cause of an object's motion, meaning an object can move without a force acting on it, but it can't speed up without a force acting on it. It can't slow down without a force acting on it, or change direction. Now, the second law of motion. Oh yeah, and remember, change of motion is acceleration, so speed up, slow down, change direction. So for the second law of motion, Isaac Newton literally said, to the change of motion is ever proportional to the motive force impressed, and is made in the direction of the right line in which that force is impressed. Let's take a look at an example.
Every day is so wonderful, and suddenly it's hard to breathe.
So if we were going to try and put this in more modern terms, we would say the change of motion, or the acceleration, is proportional to the force and in the same direction. So when James Franco is about to get punched, his face is at rest. Then he gets punched, experiencing a force. The acceleration, or the change in motion of his face, is proportional to that force and in the same direction. So he will speed up from rest to some velocity in the exact same direction as that force. Let's put this in our law of motion box for number 2. The change of motion is proportional to the force and in the same direction. Okay, so what does this tell us about force? Well, this one's a little bit complicated. So acceleration is directly proportional to the force. That's what we just said. More force means more acceleration. And if I was to write an equation, I would say acceleration equals, and if it's direct proportion, then it goes on top. So the acceleration is equal to force. But remember that acceleration is indirectly proportional to the mass, like our bowling ball kickball example. So more mass means less acceleration, just like the bowling ball. There was more mass, and so it experienced less acceleration from the force of the kick. That means we put mass on the bottom of our fraction because it's an indirect proportion. So this equation, acceleration is equal to force divided by mass, and notice that the acceleration is a vector, so it has an arrow above it, and the force is also a vector because it'll have that same direction, but mass is not, it's a scalar, so there's no arrow. This equation is usually rewritten to put force by itself. And we do that by multiplying both sides by m. So what we get is F equals ma. Now, this is what we're going to write in our box for the second concept of force. Force changes motion, and now we know that force is the product of mass and acceleration. So in your little box, on number 2, for what is force, right? Force is the product of mass and acceleration. Okay, good. Now let's talk about the third. Actually, let's do an example first. What is the force of a kick that accelerates a 0.5 kilogram ball by 12 meters per second squared? Well, F equals ma. So to find the force, all I need to do is take the mass, 0.5 kilograms, and multiply it by the acceleration, 12 meters per second squared. When I do that, I'm going to get 6 kilograms times meters per second squared. Now, you can use that unit, but in honor of Isaac Newton, we typically say that a kilogram times a meter per second squared is called a newton, and we use the capital N to describe it. All right, At this point, I want you to pause the video and see if you can solve these two problems. A 10 Newton force accelerates a 5 kilogram object by how much? And what is the mass of an object if a 6 Newton force accelerates the object by 2 meters per second squared? Okay, hopefully you paused the video and tried to see if you can solve it, or you just sat there awkwardly and waited for this to happen. To figure out a 10 Newton force accelerating by how much, I would say, okay, well, let's write our equation like this. Acceleration equals force divided by mass. And the force is 10 newtons, the mass is 5 kilograms, so when I expand that newton, it's a kilogram times a meter per second squared, and so now I can see the kilograms, they cancel out. And I get 10 meters per second squared divided by 5, which is 2 meters per second squared. For the mass of an object, if a 6 Newton force accelerates the object by 2 meters per second squared, I would rewrite my equation so that I have mass equals force divided by acceleration. Now, 6 newtons is the force, and 2 meters per second squared is the acceleration. Again, if I take that newton and expand it so that I have a kilogram times a meter per second squared, then I can see what happens to the units. The meters per second squared cancel out. And I get 6 kilograms over 2, which is 3 kilograms. Congratulations. That's how you use the equation F equals ma. Okay, now the third law of motion, our final law of motion. What Isaac Newton literally said was, to every action there is always opposed an equal reaction, or the mutual action of two bodies upon each other are always equal and directed to contrary parts. So let's look at an example of this.
Is that any good or not? Yeah, it's pretty good.
It's like one of those Newton's cradle things. The ball just stops dead and then your head carries on at the same speed.
That's ridiculous.
So if we were going to put this in more modern terms, we would say when one object acts on another, both objects experience the same force in opposite directions. So in the example of the face, the ball has a velocity. The soccer ball has a velocity, but this person's face does not. Eventually, the ball is going to hit this dude in the face. When that happens, the face is experiencing a force and therefore a change of motion or an acceleration to the right. Now, this speeds up the slow-mo guy's face, but the exact same force is experienced by the soccer ball in the opposite direction. What does that do to the soccer ball? Well, the soccer ball is moving to the right, and so this force to the left, and therefore the change in motion or the acceleration to the left, it just slows the ball so that it stops dead in its tracks. And the person's face speeds up from rest to some velocity off to the right. So in our box, let's write that in the law of motion spot for number 3. When one object acts on another, both objects experience the same force in opposite directions. Okay, great. So what does this tell us about force? Well, force changes motion. It's the product of mass and acceleration, and force is experienced equally by two objects in opposite directions. And this is always true. Force is experienced equally by two objects in opposite directions. Make sure you write that in the bottom right-hand corner of your box. So this means that force always exists in pairs. If something is changing its motion, there is another object that is also changing its motion in the opposite way. So if you are going to push off of something to experience a force up, something else has to experience a force down, like the ground. If you want to change your motion by speeding up, then you have to push down on the ground, and the ground experiences that downward push. Now, what's confusing about this is that sometimes the change of motion is not the same. Even though the force is the same, the change of motion isn't the same. With the example of the soccer ball in the face, they had about the same mass or inertia, and therefore the change in motion was pretty similar. One went to a dead stop, and the other sped up to about the same speed as the soccer ball. Let's do an example where two objects are going to experience the same force but different accelerations. A 100 kilogram astronaut pushes off a 1200 kilogram asteroid in space with a 600 Newton force. What acceleration does each object experience? Okay, so here I have the astronaut pushing off of an asteroid. This obviously isn't to scale, but the astronaut is much less massive than the asteroid. Like by a lot. 100 kilograms is much smaller than 1,200 kilograms. And the astronaut pushes with a 600 Newton force. So at the exact same time that happens, if we want to find the acceleration, we just take that force and divide it by the mass of the asteroid. So that force of 600 newtons divided by 1,200 kilograms, that's the mass of the asteroid. This is going to give us the acceleration of the asteroid, which, remember, we have to take that newton and turn it into a kilogram times meter per second squared. Now I can see that the kilograms cancel out. And 600 over 1,200 is 1/2, or 0.5 meters per second squared. So the change in motion, or the acceleration of the asteroid, is 0.5, which is a relatively small acceleration. Assuming the asteroid is at rest when this force is applied, then after 1 second, the velocity of the asteroid will be 0.5 meters per second. Then after another, it'll be 1 meter per second. After another second, 1.5 meters per second, and so forth. The astronaut's acceleration, how are we going to find that? Well, we can't find the astronaut's acceleration until we understand that that 600 newtons of force is felt by both the asteroid and the astronaut. So to find the acceleration of the astronaut, I just need to take that 600 Newton force and divide it by 100 kilograms. But I have to be careful to make this a negative 600 Newton force. And here I've got kilogram times meters per second squared as a Newton because we have to expand it. So that negative is important. It experiences that 600 Newtons of force in the opposite direction. So now when I divide negative 600 kilogram meters per second squared by 100 kilograms, the kilograms cancel out, and I get negative 600 over 100, which is negative 6 meters per second squared. So this is a much larger acceleration. In fact, it's 12 times bigger than the asteroid's acceleration. So if I was to draw the vector for the astronaut's acceleration, it's going to be bigger than the acceleration for the asteroid. What this means is that the astronaut, because of this force, is going to speed up to the left much more than the asteroid does. In fact, after 1 second, the astronaut's going to be going negative 6 meters per second. After 2 seconds, it's going to be going 12 meters per second. 3 seconds, it's going to go 18. He is speeding up much more from this force than the asteroid. So we would expect, after this push, for the asteroid to be moving with a relatively slow velocity and the astronaut to be moving with a much larger velocity. And that's what happens. So, equal and opposite force, but change of motion depends on mass. That's kind of an important concept, and we'll explore it more in future lessons. This video is over.